Okay, in today's lecture, we are going to talk about another concept in hydrology, which is called catchment, or watershed, or water basin, or river basin, as a main control volume in hydrological studies. Okay, so a catchment or watershed is the area that drains into a lake, stream, or river via streams or ditches directly over the ground surface or through the ground. You see here, for example, we have a part or a perspective of a land, okay, that when we have a rainfall on it, we sure that all the runoff, you know the meaning of runoff now, that collects in a river and comes to one outlet. Therefore, the entire landscape that contributed to the runoff of those rainfall in one point is called catchment or watershed, and also is called basin or river basin. It could be very large, it could be small, and based on its size, we divide catchment in sub-catchments and micro-scale catchment, macro-scale catchments, and so many other categories that we will see in this lecture. Here you see, for example, a lake and different rivers that comes to a lake. Therefore, this area starting from the top of mountains up to the lake is called, for example, catchment of this lake or watershed of this lake. Assume this is, for example, one lake, and there are several rivers in the one lake basins that comes to one lake, and those entire area that brings or drain, we say drains the water, rainwater onto the lake is called the watershed or catchment of one lake. Therefore, to know to find the catchment, you need to first know the outlet. For example, the outlet of this catchment is one lake. Why? Because all the water comes to the lake one. And for example, this is another catchment. This is a main river and some tributaries we have. All the rainfall that comes into this area goes to this point, which is called outlet, and therefore the entire area is called catchment of this outlet, or catchment of the main of the river. For example, if it is, for example, Aksu River, this area is called Aksu River catchment or Aksu River watershed. Why we need this concept? Because when we are going to do our calculations in hydrology, we need to know our control volume. You saw from the beginning of fluid mechanics and also hydrology course, I always talk about control volume, control volume. In hydrology, our control volume could be a catchment, a big catchment, a large watershed, which means watersheds or catchments of large rivers like Euphrates, Tigris, Büyük Menderes, Çoruh. These are large rivers in Turkey, and or a small river, or yeah, we can say small rivers that, or a part of catchment of large rivers, which is called subbasin, can be also our study area or our control volume. In hydrology, catchment is a logical unit of focus for studying the movement of water within the hydrological cycle. Because the majority of water that discharged from the catchment outlet originated as precipitation falling on the catchment. Let me see the following. Yeah, I will talk about more about physical characteristics of catchment in this slide. Let's come back to here and continue from this slide. Here you see my control volume or catchment, and assume that I have a rainfall shown by P. Okay, I have rainfall in this catchment. Well, what will be happen based on hydrological cycle that you studied last week? Amount of water will go to groundwater, yes, because of uh, the ground is made by soil, and therefore it is possible that water moves downward into the ground. Therefore, we will have an output like G. This is my input because rainfall is something, or precipitation, P precipitation, comes to the catchment from atmosphere. And also I can have here in the catchment, I definitely have some trees, green areas, agricultural lands, and also I have a soil, I have some rivers, you see rivers, small streams also, and therefore some amount of water in the rivers or some water that comes from rainfall can be evaporated from the catchment. Or we can say we have an output of evapotranspiration that we showed by ET. Yes. So ET is evapotranspiration, some amount of water in the catchment that's evaporated from the lakes, from the rivers, from the soil, and also transpiration from trees and plants in the catchment. This is therefore the output, and we know that water comes from the river. Some rainfall goes directly into the river system or river network and goes out as a runoff. Okay, goes out from this point, which is called output, as a runoff. Therefore, in my catchment, I can show the inputs and outputs into the catchment. If I can show it, I can write water balance equation that we studied last section. Let's see how we write. Do you remember water balance equation? In last session, water balance equation in very simple form was this one. For example, input minus output equals to delta S, or input minus output equals to rate of change of storage. This was storage. Let's come back here and therefore write the water balance equation for this catchment. We'll see what we have. The water balance equation for this catchment, we said input minus output. What is the input here? We have just precipitation as the input. The outputs are rainfall, groundwater, and evapotranspiration. For a given time, for example, 1 day, everything happened in 1 day. Therefore, delta T can be, it should be equal to delta S over delta T. But for a given time, for example, 1 day, we can remove delta T and we can say that input minus output equals to change the amount of water storage in the catchment. This equation will help us to solve so many questions in hydrology. And some example you will see in this lecture, and also we saw one example in previous lecture. In that example, in the example that I solved last session, we talked about the catchment of a dam reservoir. Now we will talk about catchment of a river. Assume this is a river, okay? As in the previous example you saw, it has a catchment. You see this yellow dash line are the boundaries of the catchment. Why boundaries? Because if rain goes out of this boundary, it does not come to this point because my outlet is here. Let me show in this way. Yeah, for example, this rain, you know that you see this rain when falls here, it moves anywhere and finally reaches in a stream, and it moves from different points, and finally, yeah, if it does not evaporate it, it comes to outlet. It is called what? Outlet. Outlet. We can sometimes show it out. And assume that we also have rain here, okay? Rain this point. The raindrop that comes this point never comes here. It goes to another place or another output, and therefore we have a boundary like this yellow line. This is my boundary, okay? Which is also called watershed divide or water divide. You should know this term also. Water divide or watershed divide is boundaries of a catchment or watershed. But you see, the this point shown here also, or some other point in watershed divide, because when we have rainfall just left of the boundary, the water moves in this catchment. In this side, it moves to another catchment. Can you guess in any catchment where is the location of watershed divide? As you see in the figure, it is always top of the mountains, top of the or locations that have higher elevations. Okay, because water always moves from high elevation to lower elevation, and the deepest point of a watershed or is a valley, which is commonly our river course. And as you see in a catchment, we have different kind of water bodies like a wetland or a lake, rivers, plants, even cities. For a big catchment, there it could be a big. Another assume this part could be a city. This part, and you can have some structures like dam here, for example, a bridge here. All these components are a part of catchment, and they have their own role in water balance in a catchment. Now, I think you understood what does the catchment mean and why we use catchment, because what we are going to extract to use in the water balance equation all depends on the interactions of water in at different parts of this catchment, with interaction with soil, interaction with atmosphere, which could be, for example, rainfall, evaporation, transpiration, and so on. So let's go to the example to see how we use water balance equation to solve a problem. In a given year, delta T 1 year, okay, is given. A catchment with an area of 2,500 kilometers square, this catchment, for example, received 130 centimeters of precipitation. The average flow rate measured in the river, the average flow rate, look, average one, flow rate, in the river draining in the catchment was in the river draining in the catchment. It means that discharge flow rate, I already told discharge, okay? The average discharge at output is 30 cubic per second. Now the question asks, how much runoff reached the river for the year? What is the amount of runoff for the river for that watershed in a year? in cubic meter, it should be solved. Okay, let me remove this part, and now with this given information, we are going to find how much runoff reached the river. It means that during this year, okay, we have a rainfall event, total of rainfall amount of 130 centimeter. And area, catchment area is given, and discharge, the average discharge is given. Now the question is simply ask, okay, what was the total amount of water in the river, runoff, you can say water, runoff in the river in terms of cubic meter. We have discharge, mean annual discharge, average annual discharge we have. We just need to play with the units, dimensions. Instead of cubic meter per second, we need to have cubic meter. You might guess what we should do. We should multiply this value, yeah, to the seconds, number of seconds in a year. A year has 365 days, 24 hours, 60 minutes, and 60 seconds. Therefore, if you multiply this value to 30, it shows you the volume, runoff volume, that during the last year received to the outlet, this point. Okay, any question? Let's see in the second part of the question, what is our unknown? The question says, estimate the amount of water lost due to combined effect of evapotranspiration and infiltration to groundwater. This part of the question reveals a fact in the watershed, that what we received as a rainfall during the last year, during the 1 year of the given year, all those rainfall does not transform to runoff. And the question in this part says, yeah, there was infiltration and also evapotranspiration. This is the fact. In every catchment we have definitely evapotranspiration and infiltration. Now we have to find, or the question asked us to find those combined value, those combined effects of evapotranspiration and infiltration, which is in total called water loss. Now we have one input, precipitation. We have one input, precipitation. We know the output. This is my output, yeah, runoff. We know that in water balance we have some other output. The question says that the output is evapotranspiration and infiltration. So I need to find any component of water balance equation. Precipitation, or my input I, equals to the amount of precipitation that reaches to entire catchment. You can find in this way. 130 centimeter precipitation, when received to the entire catchment, it would be around this value, and the unit is cubic meter, because my output, you see my output is cubic meter, and I can find I should transfer the unit of my input to cubic meter. And the question, you see, the question asked us to find the combined evaporation and infiltration in cubic meter. So this is my input in cubic meter, and this is my equation, water balance equation. Input minus outputs equals to delta S. Losses, the question outputs in general, we have these two outputs, groundwater and evapotranspiration, and delta S equals is here 0 because the question does not say there is a reservoir, there is increasing amount of water in the catchment. Therefore, considering these these one equation, the given one principal equation, the given information, I can write this equation P minus R equals to losses. Therefore, losses, which is the combined effect of UCG and ET, equals to precipitation minus runoff, which runoff you have here. Therefore, the amount of loss can be calculated in this form. Okay, now you know the concept of catchment and how we can use water balance in a catchment. But there is still a question, how we define a catchment on a land, catchment or basin, okay? In order to determine catchment, as I told you, need to know the peak of mountains or high elevation location, and you should know the location of valleys. The valleys are commonly shows our river network, and mountains are commonly shows what watershed divide or watershed boundaries. If we connect those river networks together, and if we connect the top of mountains together, then we will have catchments on different maps or digital elevation maps. This is a map of landscape, or which we say is topography map, topography of a location. And you can guess that these are, for example, these prominent points shows mountains. For example, it could be mountain here, could be the top of a mountain, and some other some valleys are also known here. Now I'm going to show you how I can find the catchment. The first step is to show our outlet. Where is the outlet? Then I can find drainage basin or watershed or catchment of that outlet. Let's assume just we are going to study water balance in this part of this topography map, okay? So I should find or determine, actually I should determine my outlet. I maximize, or I zoomed in this part, I zoom in this part, and this is the zoomed in this part, zoomed map of my previous map. And the first step is to consider or identify an output. This is my outlet or output point. Okay, this is my output. It could be any point in the catchment that commonly are in valleys or on a stream. After showing your output, you should connect the low elevation areas, which is called river network. Look, you see, maybe you can ask where I can know that those lines are the lines that have the lowest elevation by considering the color of the map. You see in this map, dark colors shows deep points, low elevation areas, but light colors show the high elevation areas. Therefore, I'm going to connect dark colors together. Let show you again. When I connect them, what will be happen? You see, when you connect those dark colors together, it creates your watershed river network. River network, one of them, which is the longest one, is generally called main channel. The others called tributaries or branches. Now I have to connect the top of mountains together in order to show where is the water divide or where is the boundaries of this catchment. Look. And by connection of those top points together, the catchment boundary is created. Now, after creating catchment boundary, you can calculate area of the catchment, and this area is the important parameter that we use in previous example, for example, to solve some problems. And when you have the area of the catchment or shape of the catchment, you see it has a shape. You can calculate its average slope, or you can find how much area is, for example, green area, how much is urban area, and so many other investigation can be done in catchment that you might use it to solve any hydrological problem in your catchment. In other words, the watershed is our control volume to use the water balance equation on it. So here you see, for example, as I told, we have macro scale catchments and micro scale catchments. A catchment, can you find some catchments here? Definitely now you know. I told you that the deep points here, for example, deep points is your valley, and if you connect the peaks, it gives you, for example, what? It gives you water divide. Look, this is one catchment. If I have a rainfall here, all of those rainfall will come and will move from here. The other catchment, maybe, yeah, let me show you here, for example, myself. For example, I assume this is, here is my output, and I want to find the catchment. The concept is first show the valley. Let's show the valley or deepest point. It seems that this is the valley, yes? Look, deepest points. Maybe I have such a deepest points. Okay. Where is the peaks? Let's show the peaks with yellow, for example. And this line, I hope you can follow me. Yeah, look, these are top. But it is approximate. It is approximation, for example. I approximate this. Okay, this is, for example, another catchment. It means that if I have a rainfall, what comes into this area, all into this area, all the rainfall finally will reach to the output. So these are small sub-catchments. These are all sub-catchments of a bigger catchment. Why a bigger catchment? Look, for example, let me show you another bigger catchment. By if I consider for example, some places around here, I can say that I have another catchment like this, for example, like this, another catchment like this. You see that all the water that comes either here, 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 finally moves to here. Therefore, this yellow is subcatchment of the bigger one. Or, yeah, we say sub-basin, basin, subcatchment, or catchment. This figure shows catchment of Choru River. Here is Black Sea, and you see that some information about main river. This is main Choru River. There are some other information on this map that shows you see Choruh Basin, the green area that shows how the shape of Choruh catchment. It means that water comes from these water divides. Any rain comes here, finally passes this point. This is the outlet. Yeah, here is the outlet of Choru River to the Black Sea, which is in Georgia, I think, if I'm not wrong. It should be in Georgia, Batumi. Yeah, am I right? The other, yeah, this is example of a large catchment. Several provinces are in this catchment. Or here you see the catchment of Euphrates River. That you see Euphrates River. That starts from the, I have boundaries of water boundaries or watershed divide of Euphrates River, which has the same divide with Choru Basin watershed, some places around here. And the green, this green area shows Tigris River. And with, this is called large scale watershed, like Euphrates River catchment. Again, here we emphasize why we need to study catchments and water balance at catchment scale. The answers are flowing water, the dominant agent in shaping the landscape. Yeah, because all the water comes to one point in that landscape. Absolutely essential use as a water source. Yeah, catchment is also water source, because rivers, lakes, wetlands are always in those catchments. Almost as important in transportation, generation of electricity, and recreation. If you want to, for example, make a hydropower, a small or big one, you have to know the catchment, its catchment area, how much rainfall comes to that catchment, how much water, how many river network, what is the shape of river network, and so many other features should be known to do or to construct a hydropower and or to do some recreational activities. In flood, they are our greatest life-taking geologic hazard. Yeah, flood is the most important and dangerous natural hazard, and to mitigate its impact, you have to know information about the catchment, biological productivity like fish farming and so many other things are done in catchment scale. Rivers are the source of most marine sediment. Yeah, when some catchments are the output or outlet of the catchments are a river, the sediment that comes from the river and goes to the sea or oceans should be considered well to keep the beaches safe for tourism objectives. Okay, this is the end of chapter 1. And I would like to receive any question if you have. Any question? No.
No, sir. Thank
Okay, you're welcome. So just I would like to give you 20 minutes break, or let's say 15 minutes break. Then I will start chapter 2, precipitation. Now is 11:20. I will see you 11:35. Is it okay?
Okay, Professor.
Okay, see you at 11:45.